talking about horizontal asymptotes.
Yeah. That's right. We just finished vertical asymptotes. Let's talk about horizontal asymptotes. There's 3 different ways that they occur, and you've just really got to run through this enough to commit it to memory. Case 1, if you're given some rational function, p of x divided by q of x, and your denominator, q of x, has a higher degree than p of x. This is considered case 1. If your denominator has a polynomial that's a higher degree than the polynomial in your numerator. If that's the case, then the horizontal asymptote is the line y equals 0. Which is essentially the x-axis. The equation y equals 0 is just the x-axis. So a quick example 4 here. What? Oh, that was example 2. All right. Example 3. We're actually going to find vertical and horizontal asymptotes. So if the function r of x is equal to x plus 2 over x squared minus x minus 20. I know I'm going super fast here, but just try to keep up. The first thing you're going to want to do is factor. So the denominator factors into x minus 5 times x plus 4. The reason for factoring the denominator is that will tell you, which asymptotes will that tell you? The denominator. The vertical asymptote. Okay? So the vertical asymptotes are the vertical lines x equals 5 and x equals negative 4. Okay? Now we have to take a look, and I would go back to the original form of the function, not the factored form. Consider the degrees of both the numerator and the denominator. The denominator has a higher degree than the numerator, correct? The denominator is an x squared polynomial. The numerator is x to the 1. So that fits underneath this classification. Q of x has a higher degree than p of x. That means the horizontal asymptote is the line y equals 0. Now, even though we're not ready to graph this whole function, I want you to at least draw a graph and put the asymptotes on there. So draw a graph, put a vertical asymptote at 5, another one at negative 4, and then put your horizontal asymptote at y equals 0. Again, that's just the x-axis. So that's where your asymptotes would be. What we're getting to here in a few minutes, after you graph the asymptotes, you're going to find the intercepts, the y-intercept, and the x-intercepts, if there are any. But that's a couple of steps ahead. But this is how you start. You find your vertical, your horizontal asymptotes, you plot those on the graph, then move on to step 2. What's step 2? I just said it 30 seconds ago. Intercepts. You find the y-intercept and the x-intercept. Step 3 is trying to figure out what the graph looks like after that, but that's in a few minutes. Okay? Let's do case 2. And we're still talking about horizontal asymptotes. For case 2, yeah.
So in case 1, you said that the degree has to be higher?
The degree in the denominator has to be higher than the degree in the numerator.
Okay. So that'd be like an x to the first power at the top and an x second power at the bottom.
Like this one. Yeah, like.
Oh. Okay, I get it now.
You got it? Case 2 starts the same way. Given some rational function r of x equals p of x over q of x, but this time the degrees are going to be a little bit different than what we described in case 1. In case 2, P of x and Q of x have the same degree. In this case, then the horizontal asymptote is the ratio of the leading coefficients. Here's what that means. Same direct. Is it? It is 4, right?
Yes.
Yeah. Find all asymptotes. That means vertical and horizontal. So this time your function is r of x equals 2x squared minus x minus 3 all over x squared plus 7x plus 10. They have equal degree now, right? The numerator and denominator have equal degree. Let's start with the vertical asymptotes though, instead of horizontal. You need to factor. You actually should write everything in factor form, not just the denominator. So let's factor the denominator first. That's x plus 2 times x plus 5. Numerator is a bit trickier to factor. It's 2x minus 3 times x plus 1. I've done a lot of factoring, so I'm very fast at it. Do you remember how to factor these, you guys? You do know how. You do have to know how to factor this.
Yeah.
You times 2 times negative. What's 2 times negative 3? Okay, now you need 2 factors of negative 6 that add to negative 1. Negative 3 and positive 2. Now you take the original polynomial or the original quadratic and split this middle term up into these two. So this is going to be 2x squared minus 3x plus 2x minus 3. This is called factoring by grouping. Then you group the first 2 terms and you group the last 2 terms together. From the first group you factor out an x. That leaves you a 2x minus 3. From the second group, the only thing you can factor out is a plus 1, and that still leaves you a 2x minus 3. Because you have a 2x minus 3 and a 2x minus 3, that's a common factor now. So one of your factors is 2x minus 3. The other one consists of the terms that were factored out here and here, x plus 1. So it's 2x minus 3 times x plus 1.
Can you just make a plain way?
Yeah, you can. Yeah, yeah. It doesn't always work, but it is sometimes a faster way. Anyway, what are the vertical asymptotes? From the denominator, it's x equals negative 2, x equals negative 5. Now watch what happens here with the horizontal asymptote. I know that definition seems confusing, but it really isn't. Okay? If they have the same degree, which they do, right? Then you take a look at their leading coefficients. What is a leading coefficient? It's the numbers at the very front. Okay, so here we have a 1 and here we have a 2. Ratio means divide. If you divide the leading coefficients, what do you get? 2. 2 over 1. So that's the horizontal asymptote. The horizontal asymptote is the line y equals 2. If you take the leading coefficients and divide them, that's what the word ratio means. Okay, so now if you were to start graphing this, again, we don't know enough to graph all of it, but we can at least put the asymptotes on there. We have 1 at -2. We have 1 at -5. Those are your vertical asymptotes. Your horizontal asymptote is going to be right here at +2. So those are your asymptotes. Yeah?
You say how you graph the horizontal line?
You take the ratio means divide, so you take the ratio of the leading coefficients. Leading coefficients are the coefficients in the very front. 2 divided by 1. Does that answer your question? Okay. Case 3. You guys are clever. You can probably figure it out. What's case 3 going to be? Yes. When the numerator has a higher degree. So given r of x equals p of x over q of x, and this time p of x has a higher degree. Than q of x. If p of x has a higher degree than q of x, then there is no horizontal asymptote. So all you would have to plot are your vertical asymptotes in that case. There is no horizontal asymptote. Okay? So there's really not much we do there with horizontal asymptotes at least. Let's go on to intercepts. I think we can do this with only one example, finding intercepts. Finding intercepts is easy. So let's use the equation that we had. Where were you? Back in example 3. Let's use that function that we had in example 3. So x plus 2 over x minus, okay. So this is example 5. R of x equals x plus 2 plus it. And since we already have a factor, let's just write it in factor form. It was x minus 5 times x plus 4. We're already halfway done. We have the asymptotes on there already. What we don't have are the intercepts. Let's do y-intercepts first. You already know how to do this, or you should know. I've told you 3 or 4 times. It's the same for any type of function, rational function, polynomial functions, any function. You find the y-intercept the same way. You let x equal 0. All x's, let x equal 0. So turn all your x's into zeros. In the numerator, if the x is 0, you're going to get a 2. In the denominator, if x is 0, what are we going to get? We're going to get -5 times +4, which is -20. 2 divided by -20 is -110. So your y-intercept in this case is 0, -110. Okay. X-intercepts are equally as easy to find. Oh, by the way, is there ever going to be more than one y-intercept? I think I've asked this question before.
No.
Because it wouldn't be a function. There can only be one y-intercept. There may be multiple x-intercepts, but there's only going to be one y-intercept. X-intercept. You let y equal 0. Now, this is function notation, so r of x is the same as y. Now watch what happens here. If we let r of x equals 0, then we have the equation 0 equals x plus 2 over x minus 5 times x plus 4. How do we solve that now? Because we're supposed to find the value of x. Much easier than you think. Much, much easier than you think. We could cross multiply, we could, and that would work. There's actually a much quicker way. Okay. James, say what you said again. I think you're on the right track. Okay. When is a fraction? This is a fraction right here, isn't it? When is a fraction ever going to equal 0? When the numerator equals 0. If the numerator is 0, isn't the entire fraction going to be 0? You guys following this?
Yeah. So rather than looking at the entire function, just take a look at the numerator. What value of x makes the numerator equal to 0? Negative 2. Negative 2 plus 2 is 0. 0 divided by anything is going to equal what? 0. So what is the x-intercept?
Negative 2. Okay. So the x-intercept is the point negative 2 comma 0. So back in example 3, you plotted the asymptotes. Let's go ahead and plot both the asymptotes and the intercepts now. So we had a horizontal asymptote as 0. The y-intercept is negative 1/10. That's just barely below 0. It's about right there. That's about negative 1/10. Okay. And the x-intercept is negative 2. Now please listen carefully. You probably ought to write this down. A graph will never pass through vertical asymptotes. Never pass through a vertical asymptote. But your graphs can cross through horizontal asymptotes. The graph will never cross through a vertical asymptote. Never ever cross through a vertical asymptote. But quite often, graphs will cross horizontal asymptotes, especially near the origin. Let's run through what we've learned so far, because the way I've taught this are the steps you should take to graph these. What have we always done first when given a function like this? We found horizontal and vertical asymptotes, right? What did we just do as a second step? Find the y and x intercepts. That's the order you should do this when you're graphing. What's the first thing you should do? Asymptotes. Second thing? Intercepts. Okay, now we're ready for the third part, and this is generally where students who don't really understand these problems just give up. If you can at least get this far and you put the asymptotes and the intercepts, I'll give you at least half of the points on a problem like this. Okay, but figuring out what the graph looks like takes a little bit more understanding. So this is what we're going to do now. Let's actually graph these. Okay, graph a rational function. Okay, let's take a look at the example 6. R of x equals 4x minus 8 over x minus 4 times x plus 1. Let's do this in the same order we've been doing the other ones. Asymptotes first, intercepts second, and then we're going to figure out what the graph looks like after that. So For sake of time, I'm going to start to abbreviate here. VA, vertical asymptotes. What are the vertical asymptotes? X equals 4 and x equals -1. Okay, so plot those. Now HA, horizontal asymptote. It's a little bit disguised because this has already been factored, so you have to think carefully. What's the degree of the numerator compared to the degree of the denominator? The denominator really is an x squared polynomial, right, if it were multiplied back together. So Q of x has a higher degree. Q of x has a higher degree. So this is case 1. The horizontal asymptote is the line y equals 0. Thank you. So put that on there. Now we move on to the intercepts. Let's start with a y-intercept. If you let all of the x's equal 0, just be careful with your arithmetic. If all of the x's equal 0, in the numerator you're going to have a -8. In the denominator, you're going to have a -4. -8 divided by -4. So the y-intercept is the point 0, 2. X-intercept or intercepts, there could be several. It just depends on what your numerator looks like. You find the x-intercepts in this case by whatever makes the numerator equal to 0. In this case, it would be x equals 2. So your x-intercept is the point 2, 0. Now, the more you do of these types of graphs, the more that you notice patterns, especially when it's broken up with horizontal and vertical asymptotes. Okay, so just try to follow along the best you can. Yeah?
If the horizontal asymptote is at 0, then how is there an x-intercept? Because wouldn't it be the part that the graph doesn't cross?
Okay. Graphs can cross through horizontal asymptotes.
So,
Okay.
you like an open circle line?
No, because the vertical asymptotes represent where x can't equal certain values, but not horizontal asymptotes. Okay, that's why graphs never ever cross through vertical asymptotes, but they do quite often actually cross through a horizontal asymptote, because the horizontal asymptote doesn't represent domain restrictions, just vertical. Okay. The horizontal asymptote describes the end behavior of the graph as x. Let's do a little bit of the graph, and then I'll show you what I mean. Consider the right side of this graph, you guys, right here. You see where I'm circling?
Yeah.
Do you see how the graph is kind of broken up into two regions? There's this region right here, and there's this region down here. Do you see that?
Yes, I do.
Okay. Your graph has two possibilities. It's either going to be bounded in this region and look something like this, or it's going to be in the bottom region and look something like that. Why can't it have both at the same time?
It wouldn't be a function, okay? But these rational functions always have this type of a behavior when you have a graph that's broken up by a horizontal and vertical asymptote. So which one of these is it going to be? Is it going to be the top half or the bottom half? The quickest way
is just to plot points. Okay? What's the value of x beyond the vertical asymptote on the right side? We could well, where is that vertical asymptote? It's at 4. So what if we tested 5 and then we tested 6 as points? Make a quick XY chart. Quick. Put a 5 and a 6. If you plug in a 5 for x in the numerator, 5 times 4 is 20 minus 8 is 12. In the denominator, 5 minus 4 is 1. 1 plus 1 is 2. That's 12 times 2. I mean 12 divided by 2, which is 6. So the point 5 comma 6. And we actually only need one point. We don't need that other point, and here's why.
It's a decimal, that's okay. Taking a look at where that point is, would it be possible for the graph to come down like this and then eventually cross through somewhere down there? What would have to be right here in order for the graph to cross through right there? Is there an x-intercept right there? Is there an x-intercept anywhere beyond 4 on the x-axis? No. There's no x-intercept. What does that mean? The graph's not going to cross through the x-axis. And if one point is above the x-axis, isn't all the points going to be above the x-axis on that region? Are you following me here? Okay. So because of the placement of that one point, you can safely make the assumption the entire part of that graph will be above the x-axis. So that part of the graph has to look like that. And let's back up here just so we're sure. How do we know that the graph is not below the x-axis? Because one of the points is already above, and there's no x-intercept here to let the graph cross through the x-axis to go negative. So the entire portion there is above the x-axis. Yeah?
Then what's the point of like the Y-intercept?
Because there's going to be there's 3 parts of this graph. There's a part here, there's a part on this side, and there's a part in the middle. Okay? There's 3 different things happening here. We've just found one piece of the graph. Because if you go back all the way up to example 1, where were you? You see example 1 here? This graph had 2 pieces to it because there was a vertical asymptote, so there had to be pieces on both sides. Because our example has 2 vertical asymptotes, there's a piece on the right side, a piece in the middle, and a piece on the left side. There's 3 pieces. Does that make sense? So let's skip the middle part for a second, go over to the right or the left side. Okay? Again, you have the same 2 choices. Either the graph is going to look like this and be above the x-axis, or it's going to look like this and be below the x-axis. It can't be both at the same time because it wouldn't be a function. How do we know which piece it's going to be? We have to plot points again. Okay? So beyond the vertical asymptote on the left side, what's a good choice for x? We could do -2. If you plug in a -2 for all the x's, 4 times -2 is -8, minus 8 is a -16. And really, you guys, it doesn't even matter what the value of the number is. All that matters is it positive or is it negative? That's really all that matters. So if you plug in a -2 for this x, what's -2 minus 4? It's a negative number. What's -2 plus 1? That's another negative number. What's a negative times a negative, though? A positive. So you're going to be taking -16 and divide it by some positive number. And that's a negative number, right? It doesn't really matter what the value of it is. All that matters is it is a negative number. So what does that mean about this part of the graph? It has to be on the bottom. And just to clarify a few more things. Take a look at where my pencil is. As this graph approaches the vertical asymptote, why does it turn down and go and head towards negative infinity? Why doesn't it cross through the vertical asymptote? It can't, because x can't equal -1. If the graph did cross through the vertical asymptote, we would say that there's a point where x equals -1. It can't equal -1. Yeah.
So does it, we don't have to cross one point, we just have to know.
All you gotta do is know where it's positive and negative. Yeah. Now the middle piece. Okay, we still have this middle piece right here. Alright? Now, between the y-intercept and the x-intercept here, the graph is connected. Okay, so we know that at least the graph connects the x and the y-intercept. Now, let's say that the graph is crossing through the y-axis. It's nearing a vertical asymptote, so it has 2 choices. Either it comes up to positive infinity or it turns down and goes to negative infinity. As the graph approaches a vertical asymptote, those are only 2 choices. It either goes up to positive infinity or down to negative infinity. Why will it not turn down and go towards negative infinity like that? True, it's already going up. If it did turn down and head down towards negative infinity, wouldn't it have to cross to the x-axis? And is there a 0 right there to allow it to do that? There's no 0 right there. So it can't turn down and go to negative infinity. The only place it can go then is up to positive infinity. So that,
So we know this is heading up to positive infinity right here. Now what about this one here? Once it crosses through the x-axis, it can't go back up, because if it did go back up, it would have to cross through the x-axis again. And there's no 0 right there to allow it to do that. So instead of turning back up, where is it going to head? It's going to head down to negative infinity. So that's what the graph of that rational function looks like. In a way, yeah. A lot of this you have to graph using some thinking skills. You have to think logically. Okay? The asymptotes and the intercepts are found algebraically, but the graph can be found just kind of thinking your way through it. Okay? They haven't called sophomores down yet, so just stay here for a second. Let's do one more example. Example 7. Actually, you know what? I changed my mind. Sorry. That's not going to turn out to be a good one. X squared minus x minus 6. X squared plus 3x. Okay. This one's going to have to go quick. Factor the numerator into x minus 3 and x plus 2. What about that denominator? How does that factor? Good. X times x plus 3. Let's go through the steps. First step are your asymptotes, vertical and horizontal. Let's start with the vertical asymptotes. The vertical asymptotes are x equals negative 3 from this factor here. And exactly, a lot of students will get confused here, but we have another factor. So the other vertical asymptote is x equals 0. Let's move on to the horizontal asymptotes. They have equal degree. It's x squared divided by x squared. So what you have to do is look at their leading coefficients and divide. 1 divided by 1 is 1. So the horizontal asymptote is the line y equals 1. Let's move on to intercepts. Let's do the y-intercept first. Oh no.
We need all 10 graders to head down to the auditorium at this time.
Just be late to the assembly, you guys. You're going to want to stay for this one. You can show up late for the assembly. This is more important.
Will they let you in?
Yeah.
At the bottom of the.
Just don't pull me, kid.
Listen quick.
Is there a y-intercept, you guys?
There isn't. Why is that? Take a look at where one of your vertical asymptotes is. One of your vertical asymptotes is x equals 0. What is the line x equals 0? That's the y-axis, right? The line x equals 0 is your y-axis. Would it be possible if there's a vertical asymptote there to have a y-intercept? No. There's no y-intercept. Okay? X-intercepts. Now you're going to have 2 because there's 2 factors in the numerator. I'm going to shut that door or accidentally call somebody. I think I'll stop being noisy. I'm going to be a little late for the assembly. This is more important. Okay, what are the x-intercepts? Come on, quick. 3 and negative 2. Those come from the numerators. So you have negative 3 comma 0. Actually, positive 3 comma 0, sorry. And negative 2 comma 0. Let's put this all on the graph. Vertical asymptotes are at negative 3.
and a 0. That's just your y-axis. Horizontal asymptote is the line y equals 1. Okay. There is no y-intercept, so don't worry about that. Place your x-intercepts on the graph. Now let's go from right to left. This region here on the right side, we have this upper region in this top corner, and we have this region in the bottom corner. Okay? We don't even have to plot points here to figure this out. There's already a point here. You see what I'm talking about? We have this vertical asymptote here, and we have this horizontal asymptote here. That means we have either this top region or the bottom region. But because there's already an x-intercept here, the graph has to be down there. Right? Does that make sense to everybody? Okay? And along those same lines, take a look at this region to the left. We have this upper region and this lower region. If we were to say, well, the graph's got to be in this lower region, wouldn't it eventually cross the x-axis somewhere? But is there an x-intercept in this region over here? No. The absence of an x-intercept here means the graph can only be in one spot. Above, because there is no x-intercept here beyond that vertical asymptote on the left side. Yeah?
Is it always going to be opposite on the sides?
Unfortunately not. Not always. Most of the time, yes, but rarely they are going to be on the same, they're not going to be opposite, so you can't always assume that they will. But that part of the graph has to look like that. Again, why is it in the upper region and not the bottom region? There's no x-intercept there. Okay, now we have this region between the two vertical asymptotes. We have the one here and the one here. What is that looking like? We have two choices. It either comes from up here, crosses through that way, and goes like that, or it comes from up here, crosses through, and goes down like that. How do we know for sure? Here we have to plot a point. Let's plot -1 and see where it is. Okay. Plot -1 in an XY table. Okay. If you plug in a -1 for this x, -1 minus 3 is -4, -1 plus 2 is 1. Here you're going to have -1 times -1 plus 3, which is 2. What does that turn into? Positive 2. So at -1, you're at positive 2. The location of those 2 points tells us the shape of that piece of the graph in the middle. What's it looking like? Something like that. Kind of a process, but make it into a step-by-step process. Asymptotes first, intercepts second, and then think your way, you find out the other pieces of the graph.